You've talked about energy through your entire high school career. We have chemical energy, we have nuclear energy, we have solar, hydro, wind, etc. We have types of energy, like we have light as a type of energy, thermal energy in fire, we have sound energy, etc. Lots of different types. In this portion of this class, we are going to focus only on mechanical energy. And mechanical energy comes in three types. There is kinetic energy, which is the energy of motion. We have potential energy, which is the energy of position. And we have elastic potential energy, which is the energy stored in any object that has been deformed and wants to return to its original shape, like a rubber band or, especially in this class, a spring. It doesn't have to be any of those things, though. If I take a meter stick and I bend it, it is now storing potential energy, elastic potential energy, and if I let it go, that energy can be released and turn into other forms. So what is energy? Energy is the ability to do work. So these words have very specific definitions in physics. Work is to move or to change matter, and very specifically, it is to put a force on something over a distance. Now, that force and distance need to be in the same direction. You can imagine that if you have a car that's in neutral and you get behind it and you start to push, you can speed that car up and put a force over a distance, and you can do positive work. It is scalar, but it can be positive or negative. You can do work to add energy to the car, and it's going to move faster. Something I don't recommend you try, you could then run around to the front of the car, and while the car is moving this way, you could push that way and slow the car down. You can do negative work. Please don't try this. But if the car is rolling by and you come out to the side and you start to push the car and it just keeps rolling, you're not going to speed it up, you're not going to slow it down, you're not going to change its energy. So even though there's a force and a distance, you're not doing any work. It's got to be force and distance, or force and distance. It can't be force and distance, all right? It can't be perpendicular. They have to be parallel. If you have a force that is partially parallel and partially perpendicular, you can find the vector component that is parallel and use that to calculate work. If work is force times distance, well, force is in newtons and distance is in meters. The unit of work then needs to be a Newton meter. Newton meter, we gave a special name. We decided to name it after James Joule, who did a lot of work in determining the mechanical equivalent of heat, in determining that heat was a type of energy and that it could be turned into mechanical energy or vice versa. If you break it down, a Newton is a kilogram meter per second squared, and distance is another meter, so the joule must be 1 kilogram meter squared per second squared in fundamental units. Perhaps the most obvious type of mechanical energy is also the hardest to figure out, and that is kinetic energy. Kinetic energy, it should be obvious that the more massive something is, the more energy it's going to have when it's moving. It should also be obvious that the faster it's going, the more energy it's going to have when it's moving. I like to think of energy oftentimes in terms of safety. If something doesn't have any energy, then it's safe. It can't move or change you, so it's safe. The more energy it has, the more ability it has to move or change matter, and so the less safe it could be. And so if you think about it, would you rather get hit by a kindergartner walking at 1 meter per second or a freight train moving at 20 meters per second? I think that one's pretty obvious, right? More mass, more speed, more energy. But the relationship wasn't as simple as even Newton thought. Newton was shown to be wrong by a German physicist named Gottfried Leibniz, but people didn't really buy what Leibniz was selling because Newton was so famous. People just assumed if there's a disagreement, Newton has to be right. He's so smart and so famous. And after Newton's death, a French noblewoman named Émilie du Châtelet actually demonstrably proved that Newton was wrong and popularized that idea. It's very rare that Newton was wrong about anything involving mechanics, but this is a case where he had the right idea. He said that kinetic energy is mass times velocity. It turns out it's not. Kinetic energy is 1/2 times mass times velocity squared. We can do some calculus to show that, which we're not going to do here. We could also do a simple derivation using graphs, so check this out. Suppose you push a cart with an increasing force over a certain distance. Unit analysis right off tells us that the area under a force versus distance graph gives us the joule. 1/2 base height is 1/2 xf, but displacement is velocity times time. If we apply Newton's second law and then the definition of acceleration, after a little cancellation, we get kinetic energy equals 1/2 mv squared. Note that this is for a very specific circumstance. If you want to prove that it's generally true, you'll need to learn some calculus. So that's kinetic energy, 1/2 mv squared. It's on your reference tables. The next type of energy to deal with would be, let's go with potential energy. There are two types of potential energy we're going to worry about in this class. The first one is gravitational potential energy. It's exactly what it sounds like. It's the energy you have based on the fact of where you are and how heavy you are, or where an object is and how heavy an object is. It should make sense that the heavier an object is at a particular spot, the more gravitational energy it has. And the higher up it is, the more gravitational energy it has. Again, think in terms of safety. If I dropped a paperclip on your toe from 1 foot up, I think you'd think I'm very weird, but you wouldn't be too concerned about safety, right? If I drop that paperclip from a mile up, in the absence of air resistance, you're probably going to want to move your foot, right? Well, if I dropped a bowling ball on your toe from a foot up, now you're going to think I'm weird and I'm probably going to jail, right? That's going to be dangerous. All that weight, even a foot up, has way more energy than a paperclip 20 feet up or 30 feet up. So what's the relationship? Again, your reference tables has the equation. It's simply your weight times height. Weight is mg, height is h or y, and so you have weight times height is your potential energy. That one is pretty easy. The other type of potential energy we're going to deal with in this class is elastic potential energy. And that is the energy stored in any kind of object that has been deformed and then is trying to form back into its original position. So for example, if I take this meter stick, it's just a piece of wood, right? But if I take it and I bend it, it now has some potential energy. Think in terms of safety. If I brought this up near your face and then let go, whack, that would be no good, right? So potential energy, right now, it doesn't have any. If I put some stress on it and I bend it, it has potential energy, and if I let go, that potential energy can be released and turned into kinetic energy, which could then do work on things. So anything that can be bent and deformed can store potential energy. We are primarily going to focus on springs. Rubber bands behave very much like springs, but springs are a good example. Let me go grab one. Now, springs range in strength quite a bit. You can have springs like this that are pretty weak and they're pretty easy to stretch. You can have springs that are rather stronger. You can have springs that are extremely strong. These are the shocks from an old Saab. I'm not going to be able to squish or pull this in any manner that you'll be able to see on screen. So springs can range a lot. You can have springs that are super, super easy to stretch, like this old deformed Slinky. All right, so springs they range a lot. And to figure out how strong they are, you can do a simple experiment. You can take a spring and you can take a mass and you can measure the length of the spring, add a mass, and then measure how far the spring has stretched. Okay? If we call the force, the weight of this, the force, and we call the distance it stretched, the stretch distance, x, we can graph f versus x. And for pretty much any spring, you're going to end up with a straight line. The harder you pull, the more it will stretch. And this is proportional. Pull twice as hard, it'll stretch twice as far. This is known as Hooke's law. And Hooke was the head of the Royal Society in London immediately before Newton, and they did not get along at all. But anyway, so a spring, this has a pretty low spring constant. This is probably like 70, 80 newtons per meter. These I've used for many, many years. I know this is about 25 to 30 newtons per meter. This, I don't know what it is, but you can imagine how much force would be needed to compress or stretch this an entire meter. Forget it, it's huge. It might be in the millions of newtons per meter to do that. All springs, if you stretch them too far, they will deform and they won't go back to the way they were before, like that poor Slinky there. But in this class, we're going to ignore that deformation point and just pretend that our springs are at least strong enough for whatever we're planning on using them for. So this Hooke's law, F versus X, giving us a straight line. Clearly, we can take the area underneath that. We can take the slope of it. What does the slope give us? F divided by x gives us the spring constant. This is called the spring constant or the stiffness constant of the spring. So y equals mx plus b becomes F equals kx. And k is our spring constant measured in newtons per meter, sometimes newtons per centimeter. If we take the area underneath that graph, look at the units. On the y-axis we have newtons, on the x-axis we have distance. If you multiply newtons times meters, you end up with Newton meters, which are joules. That is energy. So let's look at the derivation of the spring potential energy using this simple graph. We know, of course, that a straight line has y equals mx plus b. What have we got on our y-axis? We have force. And then on our x-axis, we have the stretch distance. So that's F equals kx. Easy enough? And we take the area of this thing. But we know that F equals kx. So if we plug that in down here, we get area is equal to 1/2 x times k times x. This is the potential energy stored in the spring that has been stretched that far. So potential energy of a spring is equal to 1/2 kx squared. So there you go. Those are your three types of mechanical energy: kinetic energy, potential energy due to gravity, and elastic potential energy.